probability over here, this number is fixed. It is fixed by total energy, total volume, total number of particles of my system. This is what can change as I change E10. So if I want to maximize this probability, I have to maximize the numerator. Well, at a maximum, well, so this maximization should already ring some bells from thermodynamics. You see, here we have a system that is not initially in equilibrium. And now we are trying to maximize the probability with whatever is changing. So what does it remind you of?
Entropy.
The entropy. You see, if you have a system that is not in equilibrium, entropy is maximized. So you might already expect this probability to be somehow connected to the entropy of the system. So let me just look at what is when the probability is maximum, this derivative should be 0. When at maximum. Well, let me just take the derivative. It's the derivative of omega 1. Well, let me convert it to partial derivatives with respect to E10 times omega 2 plus derivative of omega 2 with respect to E2 0 times the derivative of E20 with respect to E1, where I call this one E20, which is determined by E10. This should be 0. There's also an omega 1. This should be 0. But you see, this is minus 1. So what we have is the omega 1 by the E10 times omega 2 should be equal to omega 1, the omega 2 by the E20. Let me also insert the quantities that I was keeping constant. I'm not changing N1. I'm not changing V1. Here in the second derivative, I'm not changing N2. I'm not changing V2. The number and the volumes are constant.
What was E10?
Well, you see, I have these two systems. Okay. I bring them in contact such that they can exchange energy. Initially, before bringing them in contact, they have energy E1, volume V1, number of particles N1. The other one has energy E2, volume V2, and number of particles N2. Now, I bring them in contact, they will be exchanging energy. The energy of the left-hand side will no longer be E1. Let's say that I look at my system at some moment, and measure its energy. Then I see that its energy is E10.
Then the probability should give us 0. Not because we are not saying E1 is a variable, but E10 is a fixed number.
No, it's a variable. You see, the energy of the left-hand side is a variable now, because they are exchanging energy. And then I am asking the question, what is the probability that the energy of the left-hand side, what that I call E1, has the value E10?
So, as far as I'm understanding, E10 is the energy of the system 1 at the equilibrium.
No, not yet. It will be. Yes, E10 is...
I shouldn't evaluate my partitions at E10, but E1.
Why not?
Because if I evaluate that at E10...
What is E10?
As far as I understand it, it's not a variable yet.
No, well, at the moment it is the variable.
Okay.
Well, you see, probably it would have been better if I called, I don't know, the E10 and E20, their initial energies.
Okay.
But since I just call them E1 and E2, then once I bring them in contact, the energy that the left-hand side might have at a given moment, I just call it E10. Since they are constantly exchanging energy, E10 will be changing, might be changing, let's say. So that's my variable. It doesn't yet have a fixed value. Now my question is, what is the value of that E10 that will maximize the probability? And since the only thing that depends on E10 is the numerator, for me it's enough to maximize the numerator. The denominator doesn't depend on E10. And when I'm trying to maximize, when the numerator is maximum, it just means that its derivative, this is E10. With respect to E10,
That was the problem.
okay, that is E10. E10 is my variable. Now let me divide both sides by omega 1 and omega 2. Multiply by omega 2. So that omega 1s will be on everything that depends on the property of the left-hand side will be on the left. Everything that depends on the properties of the right-hand side will be on the right. So 1 over omega 1, derivative of omega 1 with respect to E10 should be equal to 1 over omega 2, derivative of omega 2 with respect to E20. You see, on the left-hand side, I only have properties of the left-hand side. Left system, subsystem. On the right-hand side, I only have the properties of the right subsystem. And just like in the case of, let me also write one more line. The left-hand side is nothing but the derivative of the logarithm of omega 1 at constant number and volume. The right-hand side is just the derivative of the logarithm of omega 2 with respect to energy at constant number and volume. Remember, if we studied this system using thermodynamics, we would have ds1 by the E10 at constant number and volume should be equal to ds2 dE20 at constant number and volume. You see, they essentially are the same equation. Well, which basically tells us that somehow they have to be related. Well, we can just say that this is, let's say, beta. And that equation, just like this equation over here, told us that in equilibrium the temperature has to be uniform. This equation tells us that at equilibrium beta has to be uniform. And if two systems have the same beta, then they are in thermal equilibrium. Just like the second line.
Please, could you repeat the last thing?
You see, this is what we had for thermodynamics. So if these two systems were in equilibrium, these two derivatives pertaining to two different subsystems had to be equal. And which told us that we define this as 1 over the temperature. And temperature had to be uniform. If two systems are in equilibrium, then temperature is uniform. Their temperatures are the same. This equation is basically the same equation. We are looking at the same system. We just bring two systems in contact, let them exchange energy, and they exchange energy. When they reach equilibrium, these derivatives of the for the left-hand side and the right-hand side, they have to be the same in equilibrium. So if we call this thing beta, beta also has to be uniform in equilibrium for the most probable state, let me put it that way.
So equilibrium is the most probable state.
Well, that is a jump, at least for the time being. Well, these two equations, if you divide them side by side, they basically tell us that the change in the entropy divided by the change in the logarithm of omega, or let me write it the other way around. This is beta t at constant n and v. What is this product beta t? Well, Planck said that this was a constant. In fact, it said that it is supposed to be a universal constant. Which he called K. No, 1 over K, sorry. Yes, here there is a jump. There is no justification for that. But the previous argument tells us that they should be somehow related. Okay, that is one thing we know. Both logarithm of omega and the entropy can tell us when the system is in equilibrium or not. And in equilibrium, their derivatives with respect to energy should be uniform throughout the system. Well, let's give one more common property. They are both extensive. So what does the extensive quantity mean? It's basically if you double your system, both of them are doubled. You see, entropy is an extensive quantity. If you take one system, take another system, the entropy of the combined system is just the sum of the entropies. That's a property of the entropy from thermodynamics. Now, if we look at the omega, now if you look at omega, we said that omega is just omega 1 times omega 2. If I take the logarithm, it's the logarithm of omega 1 plus logarithm of omega 2. You see, logarithm of omega is also an extensive property. If your system consists of bringing together two different subsystems, then the logarithm of omega of the combined system will be the logarithm of omega of each one of those parts. Okay, now I'm expecting a question.
John, if I'm dividing one equation with the other, doesn't this mean I can only use this equation in that equilibrium state? I don't know.
Well, that is what we are looking at. We will be dealing exclusively with equilibrium states. In equilibrium, at least, this should be satisfied. In equilibrium, this should be satisfied. In equilibrium, that should be satisfied. We are looking at equilibrium states.
I'm confused about the multiplicity thing because, okay, like entropy, if you double it, it will double if it's extensive, right?
No, you see,
If I have more slots, then there might be more microstates in there.
entropy is extensive, like we know from thermodynamics. Now I look at this number of states, this concept of the number of microstates corresponding to the macrostate. Well, we just wrote this equation. Omega of the combined system is just the product of the omegas of each one of those systems. If I take the logarithm, then I get, okay, this logarithm of the omega of the whole system is sum of the logarithms of the number of microstates of the parts of my system. This tells me that the logarithm of omega, just like entropy, is an extensive quantity. Do you buy this claim, by the way?
It can, I cannot buy it.
You should not buy it.
No, isn't it the logarithm?
No, this is the omega, this is the total number of states.
The logarithm is the extensive thing.
Logarithm is the extensive one.
So I buy that portion.
Okay. If you buy this equation, this follows. Do you buy this equation? Omega is equal to omega 1 times omega 2.
The equation itself.
Yes.
Yes.
You shouldn't. You see, what is omega? Omega is the number of microstates of the combined system. You see, the combined system has energy E total. Okay. But omega 1 can have energy E10. Omega 2 will have energy E total minus E10. The total number of microspace is this sum over there. You see, once you bring them in contact, they will be exchanging energy. So E10 can take any value from 0 to ET, the total energy. That will be different number of different microspace corresponding to different values of E10. So the total number of microspace will be just the sum of this overall possible values of E10.
So on weight, it's in equilibrium, right?
No, it's in particular energy. If we are looking at the
A specific
composite system as a specific energy, that equation holds. Microstate equation.
Why should I look at that one?
Yes,
It's not
yes,
fixed.
but if it's in equilibrium, it starts. Yeah.
Why?
Because it won't change anymore.
Well, you see, okay, back to my claim about probability being 0 doesn't mean it will not change. E10 might change. But you see, that sum let me put a star. You see, when E1 and E20 have their equilibrium values, that number will be huge compared to the other ones. You see this probability distribution over here. For a typical system, it will have such a shape. The width over there will go as 1 over square root of n. So although we are always talking about probabilities, in fact, the probability will be 1 for one value and almost 0 otherwise. So that basically tells me that the probability is basically this number divided by this one. And only for E10 star, we have almost all the states, microstates have an energy E10 star. That's why in this sum, when E10 is equal to its equilibrium value, it will dominate by orders of magnitude all the other terms. So I can write this expression.
So does this means the system is never in equilibrium, it appears to be in equilibrium,
Now, the question is, what do you mean by equilibrium?
not changing.
Let's say, tell me a system that you think is in equilibrium.
The glass of water
Okay, the glass of water.
over 2 hours.
Over 2 hours. Okay, the glass of water over 2 hours. How precise are your equipment?
Can you repeat the question?
How precise are your equipment? Let's say, well, you are an experimentalist, right? You are working with lasers.
I tried.
You tried, okay, great. So you can try it. Send a laser through a glass of water for 2 hours and measure what is the intensity of the laser light on the other side to an accuracy of, well, how accurate can you get? Will it be constant?
No, the laser itself will change.
The laser, you see, equilibrium depends on the context. You say, is this classroom in equilibrium, in thermal equilibrium?
If you think whole universe and a class, then it's equilibrium.
Really?
All the other,
Well, you see, if you think all the universe and the classroom, in the universe there are places with temperatures of 10,000 Kelvin. And this classroom is definitely not 10,000 Kelvin, and we have been saying that in equilibrium, the temperature is uniform. This classroom is not in equilibrium with the universe. This classroom is not even in equilibrium with the Earth. If you look at it over 24 hours, the temperature will change constantly. But if I make a measurement, I don't know, I will be in this classroom for 3 hours. What I care about is, does the temperature constant through those 3 hours? More or less, yes. So for me, it's more or less in equilibrium.
Is it?
Hmm?
Fear limit? I think not.
Well, you are saying that you are 37 degrees Celsius, so how is it in equilibrium? How much energy do I exchange with my environment?
It depends on my temperature.
The temperature difference, the time, how long am I talking about? You see, if you are making a measurement for a very short amount of time, but I think, yeah, I will agree with you. This classroom is more in steady state rather than in equilibrium. But I don't know, if I look at that corner over there within my hand, I can say that that is in equilibrium, even if I'm in the vicinity, as long as my measurements do not last hours. Because within that time, my system will not be changing. They will not be changing within the precision of my measuring device. But if I take very specific, very precise equipment, I can see changes there. So if this, in that case, I will be able to measure the changes, and if we define the equilibrium as something that doesn't change, then it's not in equilibrium. But if I'm only looking with my eyes, I won't see any changes over there. So my measuring device will not be precise enough to measure the fluctuations. So I can say that that will be in equilibrium. So it depends. The question of whether a system is in equilibrium or not usually depends on how are you measuring your system? What are the important things about your system? How long are you measuring? You see, for certain systems, if I take, well, yes, you said that you are at different temperature. Okay, I'm saying all the time that in equilibrium, the system is always have the same temperature. But for example, let's take this classroom. If I take a sufficiently small segment of this classroom, that very small segment will have a uniform temperature. So that very small segment I can still treat as being in equilibrium. There will be heat exchange, so I can treat this classroom, including myself, as systems which have a local temperature. They are locally in equilibrium. Globally, it's not in equilibrium. But then I can use all the knowledge I have about equilibrium systems, applying them to these local equilibriums to study this non-equilibrium phenomena.
I mean, you use the term temperature, but it's
Already averaging value.
yeah, already an averaging value. So it depends on how local you're living, right? I mean, after some point, even temperature will not have any meaning. So how would you define
Defining is easy.
equilibrium in very small CKs, for example?
You see,
If you cannot define temperature even in those small CKs,
you see,
how-
defining is the easy part. You're a theoretician. Defining is easy. Measuring it is difficult, or creating it is the part that is difficult. The question will be, does it make sense to define the temperature? Again, I will have a short answer. We will be dealing in the thermodynamic limit. We have infinitely many particles, infinitely large systems. For those systems, these values will have a precise and correct statement. For small systems, you will get lots of variations. You see, this probability distribution, it will become narrower and narrower only for very large systems. So if you have a small system like 10 atoms, of course this probability will have a large width. You cannot ignore it anymore. Some of our conclusions will no longer be valid. Another problem that if you look at small systems that we will face, what is a derivative? Yes, you are changing the energy value and by an infinitesimal amount, etc. Well, if you apply quantum mechanics, if you have let's say a single electron, How do you change its energy? By an infinitesimal amount. It only has...
Is it even continuous?
Is it a continuous? Well, we will be taking derivatives with respect to the number of particles even. Chemical potential is the derivative with respect to the number of particles. Well, that is a discrete number. Number of particles is a discrete quantity. So what do you mean by its derivative? Well, of course, if you have 10 to the power 23 particles, changing that number by 1 is almost a continuous change. But if you have, I don't know, 10 particles, changing that number by 1 is no longer a continuous change, it's a discrete change. So you have to be aware of those problems when you are looking at systems with small degrees of freedom.
So in the multiplicity definition, the summation that's written in the case of a small system that is not continuous.
This one?
Discrete system.
No,
This for the discrete
this
system.
summation is always valid. This is the correct, exact definition.
It does not become an integration at some point? Yeah, it is
But whenever I write summation, just keep in mind that if it's a continuous variable, it's an integration. That's
so
always
this is the more general.
But I know that for macroscopic systems, there are, although many terms in this summation, only one of them contribute significantly. The other ones are negligible compared to this term. So this is again some weird property of huge numbers. Any other questions? Okay, so question. Okay, let's give a 10-minute break and we will continue.
Hocam, ben geçen hafta yine sorudaydım da gelemedim derse. Çok anlamlı. Ders notlarından takip edeceğim geçen hafta.
Ya kaydetmişim de sesi kaydetmemişim geçen hafta.
Olsun. Neden de var zaten.